Welcome to Lesson 2, titled Neural Networks, of our course on Vision Deep Learning. To revisit our curriculum, now that we have covered the introduction to AI, in which we discuss basic concepts of machine and deep learning, we'll delve deeper into deep learning and machine learning in this lesson. And in this lecture, we'll focus on the details of neural networks. In the last lesson, we briefly talked about what a neural network was, and in this lesson, we'll go deeper into the details. The lesson will concentrate on the following three key concepts. First of which being understanding machine learning. So in this section, we'll explore the theory behind machine learning, especially how neural networks serve as a tool for machine learning applications. And we will also provide a more in-depth definition of deep learning that was previously held back in the earlier lesson. Next, as introduced previously, we'll discuss the concept of a tensor, which is a fundamental element in neural networks. We will also cover gradient descent, which is a fundamental algorithm for training neural networks. For the last two topics, which involve considerable mathematics, rather than focusing on the equations, we'll focus on the intuitive understanding. And this approach will help us apply these ideas directly to coding. Don't be intimidated by the mathematical aspects. I will break down the complex topics into simpler and more digestible parts. To fully grasp the mathematical theory behind neural networks, it's beneficial to have a basic understanding of linear algebra, calculus, and basic probability theory. Let's start with the first section of the lesson, understanding machine learning. In this section, we'll first explore what machine learning is, in which we'll provide a more in-depth definition of machine learning, in which we will explain the intuitive idea of bettering representation that the mathematical equations employ. We'll also provide an explanation of what we mean by learning in machine learning. However, since our course is focused on deep learning, we'll primarily focus on the training aspect of machine learning, where the model learns from inputs of data. For a more detailed study specifically on machine learning, consider exploring machine learning courses we offer at Metacode. So, what is machine learning? We briefly discussed this in the introduction to AI, describing as a process of learning statistical rules from input data. Now, we'll delve a bit deeper to provide a more general definition of machine learning. Our previous definition holds true, but we will give a more general one. Machine learning is defined as the process of learning representations from data. So, these representations can include statistical rules among other forms. The formal definition of machine learning is the act of finding operational rules for data processing tasks when given input data and expected outcomes. To simplify, we use input data and expected outcomes to learn rules that complete specific tasks. This definition aligns closely with our previous discussion, but now we emphasize that the model uses pairs of input data and expected outcomes to derive rules that explain the relationships between variables within the dataset. Essentially, machine learning automates the process of analytical model building using algorithms that iteratively learn from data. Machine learning allows computers to find hidden insights without being explicitly programmed where to look. This iterative aspect of machine learning is important because as models are exposed to new data, they are able to independently adapt. They learn from previous computations to produce reliable, repeatable decisions and results. We can break down the elements of machine learning into three elements. Of the three, first is input data points. And this is what we feed into the model. These data points could vary widely depending on the task you're working on. Other than the tabular data that machine learning has been strong on ever since, they could be pictures or images, then videos, and voice recordings, which are all examples of unstructured data. The second component is expected outcome paired to a specific input data, which is sort of like an answer sheet. For example, if we're doing a classification task on animal pictures, an answer key would be a label saying dog, cat, specifying the answer that the data corresponds to. And in the case of medical image processing, it would be has disease or no disease, for example. And in the case of voice recordings, it will be the correct text embedded in the voice recording. Third is evaluation of algorithms. Basically, we need a way to score our models. By evaluation, we mean calculating the difference between the current output and the expected output and adjust the algorithm accordingly. This calculation typically involves a metric that is chosen based on the type of machine learning model being used. For example, in classification tasks, we might use accuracy or log loss, while in regression, we might use mean squared error or absolute error. Then, using this difference, we apply a fundamental machine learning concept known as gradient descent to adjust the algorithm accordingly. We'll describe it a little more in detail later, but to provide a brief overview, using the discrepancy between the input and the label, we refine the algorithm or model to improve its accuracy and effectiveness. By understanding these three core elements, input data points, expected outcomes paired with the input data points, and evaluation metrics. Using these, we can effectively train machine learning models to perform a variety of tasks accurately. This refinement process involves techniques such as tuning hyperparameters, adjusting learning rates, or changing the model structure to better align with the data characteristics. So, what are machine learning models? Machine learning model, quote-unquote, learns from the above three elements. So, how do we define what learning is? It is defined as the process of automatically searching useful representations of data that brings a sample data input into the model closer to the expected output. So then, what does the machine learning model do? A machine learning model actively engages in a process called feature learning or representation. This process involves automatically identifying the most informative features from raw data that are most indicative of the desired output. By adjusting its internal parameters, the model learns to map the raw input data to these learned features, which are structured in a way that optimizes the model's performance on given tasks. This process is iterative and dynamic. As the model is exposed to more data and possibly feedback, it continually refines and adjusts its parameters and the way it represents data, reducing the gap between the prediction and the actual outcome. This concept may be a little vague with just words, so let's take a look at a diagram. First, we have raw data. In this example, we have extracted two relevant variables of features from the raw data represented by X and Y. When we as humans look at it, intuitively, we can draw a line in the middle of the two sets of data points. Then, we can change the representation of these data points by transforming the coordinates to establish new sets of axes. And this process is called coordinate transformations. Then, using the new sets of axes represented by x prime and y prime, we can reclassify the data points for a better representation. So, this is what a machine learning model does mathematically to describe intuitively. To iterate, we use a dataset, extract features to classify, and we make it better by deriving new features, namely x and y, which we obtain through coordinate transform. Then, we can represent the data in a new way, which allows us to use the variables x prime and y prime to classify the data points better. And this is what a machine learning model does, explained intuitively. To iterate once again, we have a set of data points, each with a label associated with, which are red and blue in this case. And the differences or errors we calculate can be computed by finding the distance between the data point and the axes, where the definition of a distance may vary depending on the model. This data point is blue but lies on the right side of the division line, so it will have a large error associated with it. So, the algorithm evaluates or learns this way and creates a new representation. And this is what we mean by learning in machine learning. So, When we say looking for statistical rules, we are trying to find representations that can better represent the data. In our last lessons, we simply described deep learning as a subset of machine learning that utilizes deep neural networks, which allows it to operate better on structured data. Now, to provide a more in-depth definition, deep learning is defined as a new approach to machine learning. But machine learning and deep learning are similar in that they both learn meaningful representations. So up to this is the same with machine learning. The difference is that we utilize deep and successive layers to extract features from data progressively. This multi-layered approach enables the handling of complex patterns and relationships within the data, which are often missed by shallower learning models. In the last lesson, we briefly took a look at the architecture of a neural network, which consists of layers of neurons stacked one after another. As the input data passes through these layers, the neural network successfully identifies and refines features, ultimately optimizing these representations to match the final output. We use deep neural networks, as discussed in the previous lecture, which distinguishes them from traditional machine learning algorithms that might use simpler or fewer layers. So, the key takeaway is that machine learning and deep learning are similar and that they both create better representations of the data, but the difference is the usage of deep neural networks.